All right, wrapping up this chapter, we're going to talk about reactions that we already kind of know a little bit about, but specifically pointing them towards the benzylic position. Now, the benzylic position is the carbon directly attached to the benzene ring. These guys are the benzylic positions, okay? And those are what we are going to be focusing on. So remember that aromatic rings on and alkyl groups are not easily oxidized, right? Chromic acid oxidation is something that we did last year in the oxidation chapter, which was pretty much chapter 12 of our textbook, but chromic acid oxidation needed an oxygen already present, typically on the molecule. What's interesting is that benzylic positions are readily oxidized by chromic acid. What happens is that as long as you have at least one benzylic hydrogen, you will undergo oxidation. And that means is we cut off the entire chain and we oxidize that benzylic position to a carboxylic acid. Again, you do need at least one hydrogen on that benzylic position. So a tertiary carbon at the benzylic position does not work, no reaction, right? So a primary or a secondary for the benzylic carbon will undergo oxidation with chromic acid to form the same old benzylic acid, same exact molecule, right? No matter what the carbon chain looks like, oxidation will always form benzoic acid. Permanganate can also be used as an oxidizing agent. This is one that we might not remember. Permanganate was used in the dihydroxylation of an alkene. This again will do the exact same thing. You just need step number 1 with the potassium permanganate with water and heat. Because it's a slightly basic reaction, you do need step number 2 as an acid workup. No mechanisms for these, just the reaction. We saw NBS last semester, so hopefully that radical reaction will be understood. We do need to remember that one. Again, as long as you have one hydrogen there at the benzylic position, you can substitute that benzylic hydrogen for a bromine. Now, why is that good? Well, because a whole mess of reactions are brought up once we put a halogen on there, right? We can do an SN1 reaction, we can do an SN2 reaction, depending on what type of benzylic bromide we have, whether that the position is a tertiary, and so you would undergo the unimolecular reactions, or if it's a primary, then you could undergo the bimolecular reaction. Now, benzylic bromides are readily converted then, also in E1 or E2 mechanisms. And so you can do a whole mess of reactions that we did last semester. Yes, you should know those reactions from last semester, okay? So having benzene with at least one proton in the benzylic position, whether it's a primary or a secondary, right? Each one of these has at least one hydrogen. We can look and say that will be oxidized into the benzoic acid, or we can do radical bromination and we can do all sorts of substitution afterward. Now, under forceful conditions, we can take benzene and reduce it to cyclohexane. It takes a very good catalyst, such as nickel, 100 ATM and 150 degrees Celsius. Yes, that does look like a bomb to me as well. Radical forceful conditions, right? Really crazy conditions. However, alkenes can be selectively hydrogenated using our reactions from last semester. Hydrogen with platinum, palladium on carbon, any of those. We can selectively reduce still our alkenes or our non-aromatic pi bonds, okay? So you still can use H2, palladium on carbon, or platinum or nickel, as long as you don't use your pipe bomb, right? Don't use your bomb. Don't do 100 ATM at 150 degrees Celsius. Just write the actual catalyst on there. Platinum, nickel, palladium on carbon at room temperature and normal atmospheric conditions will selectively reduce alkenes and not the benzene. You want to reduce benzene? Sure. Pump up the pressure and pump up the temperature. Now, the Birch reduction is a new reaction. We didn't really cover this reaction, but it is a good reaction to do. It's similar to the dissolving metal reduction, which is why it's referencing old sections here. Now, the dissolving metal reduction was sodium and ammonia. We add methanol in here as well, just to make sure that we have a better proton donor. Okay, so let's dive through this mechanism. I just want to show it to you. I think it's really, really important to understand. There will be more important mechanisms though in the future chapters. All right, so benzene it gets donated a single electron from a sodium atom. So we're going to see our single electron arrows, right? Now what that does is it causes pi bonds to split and to cascade. So that first pi bond will join together to make an anion, right? And all the subsequent pi bonds will break up around that ring to form a radical at the bottom. Okay, so we have a radical anion, just like our previous dissolving metal reduction of sodium and ammonia of an alkyne from chapter 9. Now, boop, 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 boop. Too far. Proton transfer with the methanol. And that's how we get one hydrogen attached. So we have successfully now converted that top carbon from sp2 hybridized to sp3 hybridized. Second equivalent of sodium can then be used. Boop, 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 boop. Pop that right there with the other one. And then that anion can go and pick up another proton. So again, converting the second atom to sp3 hybridized. Nuke attack followed by proton transfer. The Birch reduction does not completely reduce the benzene ring, but it does keep the functionality of two alkenes there, but now they're not conjugated. So now those pi bonds can react in any reaction that we saw a pi bond react last semester, right, in chapter 8 or 9. So the product has two new sp3 hybridized carbons on opposite ends of the ring. If we have the presence of an electron donating group, an alkyl group, so an sp3 carbon, that usually provides some regioselectivity so that this carbon is not reduced with the electron donating group. Why? Because when we looked at the mechanism, that carbon, because it has an electron donating group, doesn't want more electrons. So it usually doesn't gain more electrons. So we usually just go right next door and start here and avoid this pi bond altogether. The presence of an electron withdrawing group, on the other hand, does the exact opposite, right? The electron withdrawing group pulls the electron density away from the benzene ring, and so therefore it's making that position and that pi bond more reactive, so that one will get reduced. Do you get my drift? You'll reduce this guy and then the opposite, that guy. Just to review, don't forget spectroscopy is really important. We're going to talk about spectroscopy when we join together in class. All of the things that we talked about with aromatic compounds still exist, right, in spectroscopy. So we still need to know about the IR. We got your benzene wiggle right there. You got your CH groups, your sp2 carbons to hydrogens, stretching vibrations of the ring, etc. We also have our NMR, again, remember, around 7 to 8 ppm for our benzene ring hydrogens. And then, yes, we do have substituents that still appear in the alkyl range of 1 to 5. Don't forget orthometaparasplitting that we had talked about before. Symmetry is really important, especially with the benzene ring hydrogens. We'll review all of this stuff when we get back into class and see some more practice problems. If you need more practice problems, they're right down there with those conceptual checkpoints, but we'll have those in class as well. So symmetry and looking at numbers of carbons is really, really important for not only carbon NMR, but proton NMR as well. Just some real life applications, buckyballs and nanotubes, and looking at things that are aromatic rings that are fused. Graphite, this is graphite. Pencils, look at that. It's just good old benzene rings, right? Now looking at graphite, the sheets that we think about that carbon takes in graphite pencils, that's how the sheets are able to be transferred onto a piece of paper and still erased, right? Graphite is this sheets of fused aromatic rings together. Diamonds, not so, right? Diamonds are the same type of idea as carbon, but they're more in crystalline form. So they're in a crystalline structure rather than sheets, which is why diamonds last a really long time, but they will slowly form. It is spontaneous. Diamonds will become graphite. It just takes billions of years. So still, I'm a hopeless romantic. My diamond ring will become a pencil. I'm a teacher. I love that. Buckyball. So if you've never heard of a buckyball is a molecule that is this 60 carbon sphere made of interlocking aromatic rings, also called the Buckmeister fullerene. It is composed of 60 carbon atoms. They don't have a lot of uses, except they were really helpful in developing the idea of nanotubes, which do have many uses. The story of buckyballs started in 1985 when in a laboratory of a British astronomer was looking at red giants, and he actually was really puzzled by these long chains of carbons that were coming out, and his instruments told him that the stars were actually emitting. And so he joined some American scientists who were studying similar chains and clusters, and they together devised an instrument to allow them to simulate the heat and pressure of a red giant star. Right, and what they came up with is this resulting structure of 60 carbons held together in a ring, and it was in roughly a spherical shape. The molecule resembled something that was theorized by an Australian physicist a little bit earlier on, and he called it the footballine, which, you know, if you think about Australia, football is soccer for us Americans. Sorry, we're the weird ones. We changed it to soccer. He didn't think it looked like kind of like a round ball, right? Like a soccer ball, but he called it a football. They thought, in 1985, they thought it looked like the geodesic domes of this architect, Buckmeister Fuller. And so they named it after Buckmeister Fuller from the 1930s architect. Really cool, really weird. But buckyballs generated a lot of excitement. They won a Nobel Prize in 1996 for this. And it just was, people started to look up ways to like generate them. And that's really where nanotubes eventually became the thing. And nanotubes are pretty cool. They are used in a lot of different applications. So cylindrical nanotubes are the descendants of the buckyballs. They can be reused in conductive plastics, energy storage, adhesives, lots of biomedical applications for drug delivery, things like that. Super cool, good old carbon and aromatic rings.